Today we're continuing our study of statistics with the topics of point estimation and confidence intervals. So last time we talked about how to draw inferences about a density based on observations sampled from that density. And the strategy that we used is called kernel density estimation. Today we'll discuss a topic which in some ways is a little simpler, where we're going to estimate values that are a single number. So for example, we might want to estimate the mean of the distribution used to generate the observations that we see. So in this first problem, we have a bit of a game. We pull in this script called mysterydistribution.jl, which is sitting in the same directory as the notebook. And it defines a function called mysteryrv. And we can call mysteryrv and get a random value. So if we call it repeatedly, we'll get different values each time. So sometimes it's between 1 and 2, sometimes it's bigger than 2. Occasionally it's even bigger than 3. It looks like it's not coming up negative. Running this cell repeatedly is getting a bit old, so let's try to see more detail by making a histogram. So we see that our distribution has this sort of spiky shape where it's 0 to the left of 0, and then it jumps up and then tapers off, and it makes a big jump again and then tapers off again, and then a third jump and then tapers off, and continues that way, sort of fading out towards infinity. And the mean of this distribution, just looking at the picture, it looks like it's going to be, somewhere here. And to approximate that from the observations, one simple thing we can do is just average the observations. So if we do it once, we get a result of about 2.29. If we do it again, it's about 2.29 again. So it seems like this is a pretty good estimate. So if we plug 2.29 into this check mean function, it's going to say, good, we got close enough. The correct mean, the actual mean used for the exact distribution that's generating these observations is 2.3. So that's quite close. To find the variance, we could again try to eyeball it from the histogram, but it's going to be very hard to do precisely. It's just the average squared distance to this mean. But what we can do instead is the same idea. We can do Monte Carlo estimation, simulating the random variable whose expectation is defined to be the variance, and computing an average. So we get a value of 1.37. If we run it again, it's 1.4, 1.42. So there's a bit more fluctuation in this one. Let's use more observations. So 1.4 looks like it's typically around 1.42. So let's check whether that checks out. Yes, so the actual variance used to generate these observations was 1.41, and that's pretty close to what we got with this Monte Carlo approach. So let's formalize this idea a bit. The mean of a distribution is a function that takes a distribution as input and then returns a single number, the mean of the distribution, as output. The variance is also a function that takes a distribution as input and returns a number as output. Sometimes we write mean of a random variable or variance of a random variable, and that just means the mean or variance of that random variable's distribution. So fundamentally, it's an operation you do on the distribution and get a single number out. So we are going to give a name to that. We're going to call it a statistical functional. And what we want to do is use a sequence of independent observations sampled from that distribution and estimate the value of that statistical functional. So we'll define an estimator, customarily denoted theta hat, to be a random variable that's defined in terms of n independent random variables that are drawn from the distribution whose value of t we're trying to estimate. So a paradigmatic example would be that t of nu is computing the mean of nu, and theta hat is the sample mean of n observations drawn from nu. So in problem 2, we're asked a few questions to help us think about this definition of a statistical functional. So suppose that x is an integer valued random variable, and t is defined to be the units digit of x. Is t a statistical functional? So in other words, we're asking ourselves, is t something that takes distributions as input and gives a number as output? And it does give a number as output. It's defined to be the units digit of an integer, and that's a number. So that part is fine. However, the thing that it takes as input is a random variable. So ultimately, this composition of t with x is mapping the sample space omega to a real number. And that's the wrong thing. Statistical functional should take a distribution as input, not an element of the sample space. Something that takes an element of the sample space as input and returns a real number as output is called a random variable. In problem B, we have a little more complicated definition. So we suppose we have a probability measure nu on the plane. So again, you want to visualize that as just a plane with some mass sitting around on it. So for example, maybe there's some mass spread around over here, and there's some mass spread around each of these points, and then there's 3 individual points where there's a little bit of probability mass just piled up right at that one point. So in your head, this is what you're imagining for nu, which is a probability measure on the plane. So t of nu is defined to be the expected squared distance between 2 points drawn independently from nu. And we're wondering, is this a statistical functional? So the domain-wise, definitely fine, because we define t of nu where nu is a distribution. So t is definitely a function that takes distributions as input. And the question is, do we get a number as output? So what is this saying to do? Find the expected squared distance between 2 points drawn independently from nu. So if this is our probability measure, we're being told to draw 2 points from nu. So maybe the first point happens to be in this patch up here, and then the second point is this one where there's some probability mass. And then we compute the squared distance between those 2 points. And that is definitely random, because we drew them at random. If we drew 2 more points, we'd get a different value. However, we're then asked to compute the expected value of that random variable. So that's going to be a number. There's some value which represents on average what you get when you pick 2 points at random from this measure. You could approximate it by drawing pairs of points independently from the measure, computing their squared distances and averaging. If we did that enough times, we'd be approximating the expectation very accurately. So anyway, t of nu in this case is defined to be a number. It takes distributions as input. So yes, this is a statistical functional. So the second question asks, suppose I get a list of observations that were drawn independently from this measure nu. So we're calling them x1 up to xn, and it's boldface because it's going to be a point in the plane, since nu is a point in the plane. So for example, maybe the first one I drew is here, that's x1. Maybe the second one I drew is this point, that's x2. The third one I drew here, that's x3, x4, and so on. So this is what to imagine in your mind. And I get to see a bunch of these. And you can imagine things I could do with this list of independent observations. If I get many of them, I start to get a pretty good idea of what this probability measure looks like. And I should be able to use that to estimate the expected square distance between 2 of these points drawn independently. But in this case, what I'm saying I'm going to do with theta hat here is ignore the second one through the last one and just look at the first one, compute its distance from the origin, and return that value as my estimator of t. And this is clearly a terrible idea. We're ignoring a bunch of information that we have about the probability measure, almost all of it. We're just looking at a single value. And we're not squaring the distance, which is supposed to be expected squared distance. Plus, if you imagine the probability mass is all in some small region that's very far away from the origin, then t is going to be pretty small because all the points we're drawing are going to be nearby each other. Yet the distance from the origin is going to be large. So there are many situations where you would get a terrible answer here. And you would expect it to be great only by pure coincidence. This is a bad estimator, but it is an estimator of t because the definition says it just needs to be a random variable defined in terms of n independently drawn observations from the distribution. So in part C, we're asked to come up with our own statistical functional, and that requires us to think a little bit about what the world of statistical functionals looks like. So we saw an example of kind of a creative statistical functional in B. We're first of all thinking about probability measures on the plane instead of just on the real number line, and then we draw independently twice from the distribution, compute the square distance and then finally compute the expectation. So that's one sort of recipe for generating statistical functionals. Draw some observations from the distribution, do some stuff with them, and then finally take an expected value. We can also define statistical functionals that don't directly involve integration. For example, if the measure is specified in terms of its cumulative distribution function, then we can compute quantiles of that distribution directly from the CDF. So for example, if we wanted to compute the median of a distribution based on its CDF, the idea is that you start at negative infinity and you move to the right until you've gobbled up half of the probability mass. So at some point you reach a place where the cumulative distribution function is equal to a half, and that point is going to be the median. Likewise, we can ask for the first quartile, which is the point on the number line where a quarter of the mass is to the left and 3/4 is to the right. And in general, we call these quantities, capital F inverse of Q, quantiles. And note that once we have some statistical functionals, we can combine them together in various ways to get other statistical functionals. For example, you could define your statistical functional to be the mean of the input distribution plus 0.7 times the median of that distribution. And you could keep making this expression bigger and so on. Once you have statistical functionals, you can combine them together numerically to get other numerical outputs. There's even one of these that has a name. It's called the interquartile range. And that's the third quartile minus the first. So again, a statistical functional is just anything you can do looking at a distribution to produce a single number as an output. And you can think about the distribution in terms of its CDF or with respect to a density or whatever representation you want to use to encode your distribution. So this is a good place to mention for context that one way that this material is sometimes discussed is called parameter estimation. So the idea is that you're assuming your distribution takes some specific form. For example, you might consider the uniform distribution on A comma B, where A and B are unknown parameters. So you don't know A and B, but you get some observations from this distribution and you want to use those to estimate A and B. And this is called parameter estimation. The reason we're describing things using statistical functionals rather than parameter estimation is that parameter estimation only makes sense for distributions that take the particular form. So if I give you a uniform distribution from A to B, then I can ask what A is and what B is, and that makes perfect sense. However, if the distribution is different from that in any way, even if it's quite close, then it doesn't make sense to talk about what A and B are. For example, if you imagine that the density function has a small gap somewhere. So this is quite close to the uniform distribution, but it has this gap, and it means that we can't meaningfully talk about what A and B are. However, in the statistical functional framework, we could define A to be the minimum functional. So it says, what's the first place on the number line we start picking up mass, starting from negative infinity? And B to be the maximum functional. Where do we stop picking up mass on the number line? So from this point of view, we can totally apply this statistical functional to this purple distribution, and we would get a min here and a max here. And so if we talk about estimating these statistical functionals of the distribution, we can do that for any distribution that we want, not necessarily just ones that fit this form. And that's going to be important for reasons that are going to show up in the next problem. So with kernel density estimation, we talked about one way of estimating a distribution. You take a 1/n probability mass and you spread it out around each point. The empirical measure is an even simpler version of that idea. You take your probability mass of 1/n and you put it exactly at the location of one of the observations. So you do that for all of the observations. Each one carries a probability mass of 1/n, and that's a measure, and we call that object the empirical measure. For example, suppose we sample from a uniform distribution on 0, 1. We get this collection of observations represented by these red dots. Let's think about what the cumulative distribution function looks like for the empirical measure. So I'm coming in from the left. I've picked up no probability mass. Once I hit this first point, now I've picked up 1 over n of the probability mass. So I move up 1 over n. And then when I hit this point, I've got 1 over n more. So I move up again, and so on. So it's just going to be a step function that moves to the left, and every time it hits a point, it jumps up by 1 over n because it's picked up that 1 over n mass. And eventually it's picked up all of the mass. And what you might notice in this picture is that the cumulative distribution function for the empirical distribution is quite close to the actual cumulative distribution function of the uniform distribution. So the cumulative distribution function for the uniform distribution is just the identity on 0, 1. So it's 0 up to here, and then it moves diagonally to this top right corner, and then on from there, because it's picking up no mass to the left of 0. Then it picks up mass at a linear rate since the mass is uniformly distributed. And then it's picked up all the mass by the time it gets to 1, and so it's just flat at 1 after that. And we'll talk about this later in more detail, but there's a theorem that's going to tell us how the cumulative distribution function of the empirical measure is actually usually going to be close in some precise sense to the cumulative distribution function of the measure used to generate those observations. So at least from this point of view, it seems quite sensible to substitute the empirical measure for the unknown true measure. And many estimators are built that way. They're called plug-in estimators. So we have a statistical functional. We want to estimate the value of it. We just take the empirical measure and plug that into the statistical functional instead. So we want t of nu, where nu is the actual distribution used to generate the observations. And we're going to approximate it with t of nu hat, where nu hat is the empirical measure. So in other words, in this picture, what we want is to plug this orange distribution into the statistical functional, but all we have is the purple distribution. And so we just plug the purple distribution in instead. And sometimes this works, and other times it doesn't. So let's answer these questions for problem 3. Is the empirical measure random? In other words, if we collect a fresh set of observations, will we get the same measure? Definitely it's random because it depends on those observations, and the observations themselves are random. They're drawn independently from the underlying measure. Is the underlying probability measure random? No. That's going to be our perspective until we get to Bayesian statistics later. Why is the empirical measure useless when it comes to estimating conditional expectation of y given x, if x and y are represented by a density function? So we alluded to this a bit when we talked about kernel density estimation. If we get some observations from the joint distribution on x comma y, and we concentrate a probability mass 1 over n at each of those observations, and then we set out to estimate the conditional expectation of y given x, then what's going to happen is that whenever we take a vertical slice, most of the time it's not going to hit any of the points. So there's going to be no probability mass on that line. So it's going to be impossible to form any sort of meaningful conditional expectation. Furthermore, even when the vertical line does happen to pass directly through one of the masses, you only get one. You don't get the benefit of having observed multiple points. This is what happens when you do a kernel density estimator with a very small bandwidth lambda. You're concentrating the mass too tightly around each point, and there are going to be many vertical lines that don't intersect any of the squares, and for which you therefore can't make a meaningful estimate of the conditional expectation of y given x. And indeed, the empirical measure is just a limit as lambda goes to 0 of the kernel density estimator. Because the kernel density estimator is smearing out the 1 over n probability mass in a small lambda box around each point. And so if you do that in a lambda box that's extremely tiny, that's pretty much the same as just leaving all the probability mass right there at that point. And that's what the empirical measure does. This last question we're asked, is the sample mean a plug-in estimator? In other words, if we form the plug-in estimator of the mean, do we get the same thing as the sample mean, where you just average the observations? And the answer is yes, because the mean of a distribution that places mass 1 over n at each point in a set of points is just the average of those points. So now we'll start talking about what it means for an estimator to be good in various ways. So one simple way to talk about whether an estimator is doing its job is to consider the bias of the estimator. So the bias of an estimator is the difference between the estimator's expected value and the value of the statistical functional that it's trying to estimate. So for example, with the sample mean, if we take the expectation of the sample mean, then the expectation distributes across the addition by linearity, and we're left with the sum of n copies of the expectation of each of these random variables, and they're identically distributed, so those are all the same. They're equal to the mean of the distribution that's generating those observations, and so we end up with the expectation for that distribution. So indeed, the expectation is equal to the value of the statistical functional that you're trying to estimate. And that means that the bias, which is the difference between those, is 0. So in problem 4, we'll look at this. If we compute the sample mean for 5 observations from the uniform distribution on 0, 1, it's not going to be a particularly good estimator in the sense of giving almost exactly the correct value each time it's run. However, it is going to be unbiased, because the times that it misses low are going to be balanced by the times that it misses high. So if we take a sample mean for 5 observations, we see that reasonably often we're quite far away from 0.5. So this is what the histogram looks like. We're not saying that the estimator is reliably close to the actual value, but we are saying that the times that it misses low and the times that it misses high balance out in expectation to give the correct value. So this estimator is unbiased, and in the picture it does appear to be unbiased. So in problem 5, we'll look at an example where an estimator is biased. So we'll talk about the sample maximum. So we'll just switch mean for maximum. And same idea, 5 observations from the uniform interval on 0, 1. And we'll make a histogram and we'll check, does this look like it's unbiased? But note that it's definitely going to be biased. We're taking uniform distribution on 0, 1. We're getting 5 observations in there. And we're taking the maximum. So that's always going to be less than 1. And the actual maximum of this distribution is 1. So we're always going to be low. So there's no way that we're going to balance left and right of the true value of the statistical functional, because all our estimates are going to be left. But let's make a picture anyway. You can use the same code. Just switch mean to maximum. So as expected, most of the time we're pretty close to 1, but we're always to the left of 1. So the expected value is going to be below 1. So dual to the concept of bias is the concept of standard error, which is just another way of saying standard deviation, but specifically in the context of thinking about estimators. So it's measuring how wide this distribution is. So this is quite a large standard error. We're frequently quite far away from the expected value of this distribution. Same idea here. We have just 5 observations, so we're not able to make a very precise estimate. In other words, the variance of this distribution is quite large. So in problem 6, we're asked to estimate the standard error of the sample maximum estimator, again with 5 observations from the uniform distribution on 0, 1. So one way to do that is with Monte Carlo estimation. So we can get a bunch of sample maxima. We can estimate the mean. Looks like it's about 5/6, and then use that to estimate the variance. So we'll plug that number in here. We'll see the variance is actually 5 over 252. So the standard error would be the square root of the variance, and it's about 0.1409. So that's representing the spread left and right of the mean for this distribution. If we look back up for a minute at the sample mean for 5 observations, the way that we would get the standard error to decrease here would be to make more observations. So 5 is not very many, and if we make more, then we can get a more accurate estimate. So if we have 500 observations instead of 5, then the mass is much more concentrated around 0.5. So this is an ideal scenario. You have a small standard error and you're unbiased. So your bias is 0, your standard error is small, and that means with high probability you're going to be quite close to the actual value. That leads to the idea of consistency, which is that an estimator theta hat is consistent if it converges to theta in probability as n goes to infinity. So in other words, the bias goes to 0. It doesn't have to be 0, but it needs to go to 0 as the number of observations goes to infinity. And the standard error goes to 0 as well as the number of observations goes to infinity. So that's true for the sample mean. You can see this probability mass concentrating more and more around 0.5. If you do even more observations, it'll be even tighter. And it's true here as well. If we make 500 observations, the probability mass is concentrating more on the right edge of the picture. So the bias is still negative. It's always negative, but it might be a very small negative value. For a very large sample size, it will be, and the variance is also going to 0. So this is another example of a consistent estimator. So both of these estimators are consistent. An example of an estimator that's not consistent would be this estimator that we defined earlier for the expected square distance, or 2 points drawn independently from a measure on the plane, where we just look at the distance from 0 of the very first point. So now let's move on to the second topic for today, which is confidence intervals. So the idea is that the estimator by itself doesn't mean very much unless you know how accurately you're expecting it to be estimating the statistical functional. For example, suppose that we have this collection of observations from some distribution. So my sample was pulled in from that script, and its values are here. So unlike in the first situation, we don't get to generate them over and over again. We just get these 10 values, and that's it. So this is more reminiscent of what happens in statistics when there's a study that's performed. The study is done, some number of observations are collected, and that's it. It's over, and you have to do your best with those observations. So if we want to estimate the mean of this distribution, we can just find the sample mean, and we get 1.925. But okay, clearly we would expect most of these digits to not be informative, just the first few. And well, really, how many of them? So suppose someone said that the underlying distribution that generated these data has a mean of 2. Does that seem plausible? I mean, maybe, because it's pretty close to 1.92, but how close really does it need to be for this to make sense? Or what about 6? 6 seems pretty far from 2. If we look at these observations, they're all to the left of 6. So maybe we would say that's less plausible. But clearly we need a more principled path forward. So one solution to this problem is to introduce a concept called confidence intervals. And the idea is it's just an estimator together with some error bars. So in other words, rather than returning a single value, we return a full interval. In other words, we return 2 random variables, one for the lower bound of our interval and one for the upper bound. And we also associate that interval with a confidence level, which we call 1 minus alpha. So we're saying the probability that that random interval traps the actual value of the statistical functional we're trying to estimate is at least 1 minus alpha. So in this problem, we're spotted the information that the my sample vector was generated by calling a function that simulates the normal distribution, but it used a mean and variance that it's not going to tell us. We have to try to estimate those values from the distribution. So we want to try to find a 95% confidence interval for the mean mu of the distribution. So this is a true value. It was used when this sample was generated, but we don't know what it is. We're trying to glean some information about that. In other words, we're trying to take this 1.92 value and move up a little bit and down a little bit in such a way that we're going to trap the actual value with a high probability, with a 95% probability. So what we're going to do is calculate the mean and the standard deviation of that list of observations. So these are estimating the mean and standard deviation of the underlying distributions. They're estimating mu and sigma. And the idea is we'll have to kind of make an assumption here, and we'll revisit this later and make it a bit more precise. But if we just pretend that this 2.29 value is the standard deviation sigma, then what we want to do, if we want to trap 95% of the probability mass, is move up and down 2 standard deviations. So this is a fact about the normal distribution that you want to have memorized. So any normal distribution with mean mu and standard deviation sigma has the property that if you move left and right 1.96 standard deviations, then you've trapped 95% of the probability mass represented by that distribution. So this 1.96 value is approximate. Sometimes people use 2 instead of 1.96. That's fine. You can work out this exact value but it's easier to just remember that value. So this is our interval. We'll start 1.96 standard deviations to the left of the mean, and we go to 1.96 standard deviations to the right of the mean, and we get this interval. And actually, I missed one thing here, which is that this mean and standard deviation are of the original distribution. We have to work out how they relate to the mean and standard deviation of 10 observations drawn from that distribution. So if the expected value of each random variable is mu, and the variance of each random variable is sigma squared, then the expectation of the mean is equal to the mean, and the variance is equal to the variance divided by the number of observations. So note here, when I distributed variance, we used the independence of the observations. So in other words, the standard deviation of the sample mean is going to be sigma over square root n. So this is the 95% confidence interval we get, from 0.51 roughly to 3.34 for that particular collection of observations. So this is a random interval that we could have proposed from the beginning when we saw this list of 10 numbers. And then if someone says, hey, do you think the actual value of the mean is 2? That's in this range, so we would not rule that out with 95% confidence. But 6 we would. 6 is outside this interval, so we're 95% sure that we trapped the true value and 6 is not in there. So that suggests that 6 is less plausible. So in problem 9, we get to take advantage of yet another function that's defined in that script called traps mean, which takes a function as an argument, and this function is supposed to take a vector x and return a confidence interval. And then traps mean is going to simulate some data and check, does this confidence interval actually trap the mean of the distribution used to generate it? So we just repeat the idea that we had above. So x consisted of these 6 observations, and the confidence interval we got was from -4 up to 13, and the actual mean was about 2, and that interval did indeed trap that mean. So this actual mean value, it's not coming from the sample, it's coming from the underlying distribution that was used to generate this sample. So this is a concrete value at the time that this x is generated. But this confidence interval is random. It's computed based on these random values here in the collection of observations. And indeed, it traps the true value in this case. So we can run it again, and we get a new distribution that has a new mean, and then that mean was used together with other details about the distribution to generate these observations. So there's more observations this time. And our confidence interval is from 0.92 up to 7, and that does trap the actual value of 3. So if we run this repeatedly, we expect to see a lot of green, indicating that we successfully trapped the value of the mean. But in this case, we didn't. And we would expect that to happen too about 5% of the time. If we're making a nice tight 95% confidence interval, then we should expect to be wrong about 5% of the time. So in this case, we returned a confidence interval from negative 5.2 to 0.3, and the actual mean was 1.6. So we missed this one. And that comes from this random sample happening to sort of sit farther to the left than it typically would for this particular distribution. So if we generated a new sample from the same distribution, then we would be trapping this mean with 95% probability. So in problem 10, we're going to be looking at the sample maximum instead of the sample mean, which means we have to think about how to form a confidence interval here. There's no normal approximation that we can use to say move up and down 2 standard deviations. As we saw, the sample maximum has a distribution which is very asymmetric. It sort of ramps up moving left to right and has the biggest density very close to the maximum. So we have a uniform distribution on 0b, so the density function looks like this. And the idea is we're going to get a bunch of observations from this distribution, and we're supposed to try to use them to figure out how to trap b, the maximum. So we see our observations, maybe they look like this, and we're going to know that the biggest one is actually smaller than b. We're also going to know that b is not smaller than that one. So the left edge of our interval should be that sample maximum. It would be wasteful to move further to the left. But then the right edge, we need to move over a little bit in order to try to trap b. If we move over too little, then we'll consistently fail to trap b, and we won't have a good confidence interval. If we move over too much, that'll be wasteful. Our interval will be wider than it needs to be. So we need to figure out approximately what does this gap look like. If we call the sample maximum m, the idea is we want to say what factor do we need to scale m up by in order to get something that's bigger than b. In other words, let's think about for any value k less than 1, what's the probability that m is less than k times b? So k represents m over b, which is the proportion of this full distance represented by the distance from 0 up to m. And the probability that m is less than or equal to k times b is the probability that when we pull n observations from this distribution, let's let n be our sample size. If we pull n observations from this distribution, the maximum is less than k times b if and only if all of those observations are less than k times b. The probability for the first observation that it's less than k times b is k times b over b. Same idea for the second observation up to the nth observation. So this is just k to the n. So if we want this probability to be equal to some small value, like let's say 5%, then we can just define k to be the nth root of 5%, and then we'll know that the probability that m over 5% to the 1 over n is less than b is 5%. In other words, if we scale up m by 5% to the 1 over n, we'll get a value which 95% of the time is bigger than b. So this should be the right edge of our confidence interval. So this function traps max is generating a uniform distribution on the interval from 0 to 96.45, and we get these observations. And the biggest observation is 78.48, it's this value. And the confidence interval returned is that value up to 105.9 roughly. And that does trap this actual maximum value. So 78 was close enough that when we divided it by 5% to the 1 over n, we managed to trap this value. And once again, if we run this a bunch of times, we're going to be trapping the actual maximum about 95% of the time, but eventually we'll fail. And in this case, for example, the biggest value we got was 25, and we got quite a few observations, and the actual maximum was over 30. So when we divided 25 by 5% to the 1 over however many observations there are there, we didn't quite get up to the actual maximum. And here, if you run this many times, you really will get very close to 95%. There's no cheating. There's no approximation happening here. This calculation we performed is exact. So unlike in this situation where we had to do this cheat of taking the standard deviation from the sample and pretending that it's actually the standard deviation, the maximum situation is in fact simpler because we can calculate everything exactly.